I work a lot on social program evaluation, which is related to inequality because usually the goals of these social programs are to reduce inequality. So it could be education programs or health programs or programs to increase labor supply for certain populations. So it's a wide variety of programs. But actually the methods are useful in many different applications. So I'll show you a few different applications. And the material is, like if you want to look for a textbook or something where you can also read about these methods, I wrote this chapter in Handbook of Labor Economics with Mike Keene and Ken Moulton. So a lot of the material that I'll show you actually appears there. And these modeling methods are called like DCDP methods, like discrete choice dynamic programming. But we're going to start with some static models and then show how the dynamic models are related to the static models. Okay, so, and over the last 25 years, these methods have really become increasingly used. So they started in the mid-1980s, but at that time computers were not very good, and so you were pretty limited as to what types of choices you could model. And then over time, as computers got to be a lot better, then the frameworks that we could analyze got to be a lot richer. Okay, so we'll start looking at some simple frameworks and then build up to some applications that are, more modern. Okay, so I wanted to distinguish between a few different approaches. I like to divide these approaches into ex-post approaches and ex-ante approaches. So if you have a social program, like let's say a job training program, and you have a treatment group, like remember Jeff is not here now, but when Jeff was talking about the treatment group and the control group, so that assumes that you already have people that went to that program. And you see them and you already observe their outcomes after the program, right? So sometimes we have that kind of data. And then the treatment effects type approach, seems entirely appropriate. What was the effect of this program versus not having it? And if you have randomization, that makes it even easier, for certain questions to just compare randomized treatment, randomized control. So I would call that ex post because we're observing data after the program already started and already ran for a while, right? But ideally, you'd like to actually design programs from the beginning before they ever get implemented, So I've worked on some programs where they pay families to send their children to school. So these are programs they started in Brazil and Mexico. They're called conditional cash transfer programs. And these programs now are in 28 different countries in the world because the initial evaluations found them to be pretty effective. But there are a lot of questions related to program design, like how much should we pay families? And children in different grades receive different amounts of money. How much should they receive if you want to achieve some objective? And then when a government is designing a program, you'd also like to know how much will it cost? How many people do we expect will actually take this program? Because usually participation is voluntary, right? So there are many questions related to program design and related to anticipated effects of the program that you would like to answer before you ever implement it. Because it's very expensive just to say, oh, let's try it out and see if it works. Because any evaluation is very expensive. So that's not completely practical to think that you can try out every variety that you'd like to know about, right? So if you want to design programs ahead of time and answer questions before the program ever is implemented, you need some way of extrapolating from historical experience to this new environment, And for some programs you can do this, and for other programs maybe not. It depends on what type of variation you have in your data that could be used to extrapolate from. Okay, so I'll show you some examples of how we can use, because these are going to be more modeling-based approaches, like not a treatment and control because you don't have a treatment group. So basically you only have a control group and you want to see how can I learn from these people who have never been in the program, what behavior would be if I modified their environment. And then also when you do any sort of model, you'd like to have a way of deciding is it a good model or not, compared to other models. Okay, so this is, so the sorry, I should have showed this slide earlier, but ex post evaluation, there are all these different methods. You know, randomization, difference in difference, matching methods, but all these methods assume you have a treatment group. You know, so I think they're perfectly fine methods, you know, but sometimes our question of interest may be different. So if we'd like to evaluate the effects of say, changing an existing program or introducing a completely new program, you know, because maybe you have some program you want to say, well, what if it operated a little bit differently? If I changed the eligibility criteria, or I changed the subsidy amount, you know, what would the effect be? And then also maybe you'd like to know long-term exposure, because usually in any sort of experimental evaluation, you only see them a few years. It's not very common to follow people for 10 years after a program, you know. But you may want to know, what if this person was in the program a long time, what would the effect be? So there are many different types of questions that the treatment effects literature is not really sufficient to answer these questions. Okay, so these are just some examples, like some pretty famous examples of models that have been used to, and these are not really social programs, but like McFadden, you know, McFadden won the Nobel Prize in 2000. He shared the prize with Heckman, actually. They won the same year. He tried to forecast the demand for the subway system in San Francisco. And of course, you can't just say, oh, let's build it here and see how many people come, because you can't move it afterwards, right? So you have to do the forecast based on data, you know, without any subway, basically. And they're doing this now I was at like a transportation conference, and they said they're building a very big metro system outside of Paris. You know, like 30 billion euro metro system. So, and they're trying to forecast the demand. If they build it here, how many people are going to use it, you know, how will real estate prices change, and things like that. So that's an example where he had a model, and he was hired to actually do these forecasts of demand and help them figure out where's the optimal placement for the subway. And then after they built the subway, they can actually check how accurate were the forecasts, you know, so they may not be entirely accurate. I think they did, you know, check that actually, but still you have to base your decision making on something, you know, that's done ahead of time. This is this famous paper in I.O., Barry, Levinson, and Pincus, where they were modeling the demand for cars based on like different features of the cars. They were actually hired by the car companies to look at the demand for cars. And then, of course, one of their main interests was, if we change the price of a car, how will that affect the demand for that car, right? And let's say if one company produces 5 different kinds of cars, they want to know how it affects the demand for their own car. You know, like if BMW increases the price of the 5 Series, how will it affect the demand for the 3 Series? You know, because they actually produce a whole portfolio of cars. Or if Japan introduces these new cars, how it affects profits of different cars. Okay, so they're not social programs, but these are all examples where you need to be able to answer questions where you don't really have just like a treatment group. You know, they never actually did it. Yeah.
Do they have any data about second-hand cars?
Yeah. Yeah, that makes it even harder. Yeah, actually in this paper, they totally ignore the second-hand. The second-hand market is basically not buying a new car. But then they have some follow-up papers where they tried to incorporate the used car market. Yeah, because people would be deciding. So that would even enlarge the space more. You could buy a new car, or you could buy a used car of different years. Yeah. Yeah. So, but to answer these questions, they're like hypothetical questions where you basically need to put more structure on the problem. You know, you can't do like a treatment effects type of approach. And this model is commonly used in the US actually to analyze the effects of mergers. Like if 2 airlines merge, like recently we had US Airways and American Airlines merged, okay? But they would use this type of model before the merger to try to understand what would the effects of a merger in the airlines do to airline prices. for example. And then the Justice Department, they decide whether to approve mergers or not. So they want to study ahead of time before the merger, what would we think the effect would be in reducing competition and changing consumer welfare. Okay, so the models, the ones I'm going to show you are more related to program evaluation. These have been some papers where they actually tried to test some of these models. So Wise had a paper of the demand for housing, and we have some programs where they give people housing subsidies, like especially poor people get like a voucher that they can use to buy better housing instead of just building public housing. They have like private subsidies. So look at how if you give people a voucher, where do they decide to live? What type of house do they decide to get? And then he analyzed different models to see which one did the best at fitting housing demand. This paper here tried to analyze the effects of a bonus on retirement. Because in the US, it's illegal to force people to retire. A lot of countries have a mandatory retirement age, that you have to retire. But in the US, they changed the law, so you're not allowed to force people to retire because of their age. In the US, at least. Some countries you are allowed. And so what they do now is they give you a bonus to get old people to leave because they want you to retire and they can't force you. So then they'll give you a bonus. And they do this even at my university. They give a bonus if you retire before age 70, and then we lose these very productive people sometimes. But what he did is he made a model where he tried to predict retirement patterns, and then he actually had a treatment group where he could observe retirement patterns, and then he could see how well does the model forecast the behavior in the treatment group. So the model was fit without using the treatment group data. And I actually also have a couple papers where we do this. Like we only use the control group, but then there actually was a treatment, and then you can say, well, how well does this model actually predict retirement patterns? And then if the model does a pretty good job, then you could maybe use that model and have more confidence in varying the bonus amount. Like what if I made the bonus bigger or smaller? How would that affect things? And this is actually Jeff's paper, where they look at a welfare bonus in, these are women on welfare in Canada, and they gave them a bonus to find a job.
What is the difference between your treatment group and control group? Can you explain?
So in this case, the control group was all the data before they brought in this retirement bonus. It was like a new program. And so then they analyzed, they fit a model of retirement only to those people when there was no program. And then they introduced the program into that model, and then they say, how would that affect retirement? And then they actually had some data that came from after the bonus was introduced, and then they could compare how well the forecast does, like as a way, because we don't really have, there's so many varieties of models you can write down, and there's not an agreement necessarily on which is the best one. So this is a good way, to test how well does the model do, and then if you're able to do pretty well, then you could have confidence to change the retirement bonus, and to analyze other types of programs. Here they were looking, there was a 2,000 Canadian dollar, I think, bonus to find a job. And they were looking whether that encourages people to go off of welfare, to get a job. And this is a paper that I did with Ken Wolfen, and this is where we were analyzing this program in Mexico, but we only fit this model on the control group, and it was a model of the decision to attend school. I mean, the children have three options. Either they stay home, they go to school, or else they work, because there's a lot of child labor in our data set. And then they introduced a subsidy that the family only gets if they put their child in school. And so then we actually used the model to model this decision making. So school, work, or home, plus we had fertility in the model. And we estimated only on the control group. And then in our data, we actually have a treatment group, because they actually did a randomized evaluation of the Mexican program. And so then we could see how the model forecasted treatment effects. So if you introduce a subsidy to go to school, what does the model predict compared to what actually happened? So that's how people like usually try to test some of these models. If you have randomization, you can pretend that you don't have randomized data, just ignore the treatment group, estimate the model only on the control group, and then see how well it forecasts behavior in the other group. Some people have done the opposite, like they only estimate the model in the treatment group, and then see how well it forecasts for the control group. You know, the Esther Duflo has a paper like that, where they give teachers it's an Indian data, where I guess they have a hard time getting teachers to go to work and teach their class, like they collect paychecks without showing up for school, the teacher. So they had a program where they paid the teacher money if they would have very good attendance. And they actually had to take a picture every day with the students to verify that they were there. And so they estimate a model of teachers deciding whether to attend school. It sounds funny, but teachers going to school. And then in the model, they could take away the subsidy, and then they compare that to the control group behavior. So these are mainly some more recent papers over the last 10 years that people have been trying to compare model implications with a randomized study. Okay, and feel free to interrupt if you have any questions. You know, you're very welcome.
I would try to implement a neural network to learn the country dates.
No, I don't think there are any papers now doing that, but there's actually, it's not a huge literature so far. So, and we don't even know, you know, each model is in a different context. So we don't even have, you know, 10 examples. I mean, there's one other paper that does a model with these same data. But for the most part, it's just like one paper on each data set. So I think there's a lot of room for like examining different approaches with the same data set, you know, to see like what works better.
So when the experiment is not a one-time subsidy, when the experiment is something like what you told about India, when it ends, it has something to look at how it influenced the behavior of the treatment group, because like first treat and after that forever, the behavior changes forever.
Yeah, well that you could do, like then you could do maybe a before after if it was not a permanent program. Although in some of the models I'll show you today, it matters whether the people know it's going to end or not. Because just knowing that because knowing what will happen in the future can affect your behavior today. But yeah, in some contexts, if it like suddenly ends, then maybe you could get a valid comparison just before and after. Yeah. Okay, I'm going to start with binary models where there's just a one decision, you know, and then show you how you can extend it to, I mean, sometimes my models have like 800 decisions or something, but we'll just start with some simple binary models. And the earliest model, these were models done in the 1980s, you know, when computers were really not very good, so it's actually very impressive what they did. They estimated a model, the decision whether to stay in the military or leave the military. So it was a dynamic model whether to re-enlist. Miller had a model whether to change occupations, like stay in the same occupation or switch to a new one. Pecos had a model whether to renew a patent. So patent is something that gives you exclusive right to produce some good, you know, but there's some probably money and then also effort to renew a patent. You know, so maybe you might want to let it optimally expire. Russ had a model to replace a bus engine. This is a paper published in Econometrica. He had this data from this one guy who owned these buses, and then his name was Harold Zucker, because he's like in the title of his paper. But I guess the bus, after the engine is worn out, they can replace it. But he had to decide, you know, whether to replace it or not. And then Wolfman had a decision just to have a child. So he had data from Malaysia where you had high child mortality. And his question was like, if a family experiences the death of a child, do they then increase their fertility afterwards? I mean, not really replacing the child, but to make up somehow for the child that died, you know? Okay. So those were kind of the earliest papers in this literature. So, and I'll show you, just start with a static model and then show you how to extend these models for dynamic models. Okay, so there's going to be a binary choice where they just choose 0 or 1, right? And it has a t subscript, but for now we'll just consider one time period and then extend it. Okay. You know, it could be attend the training program, stay in school, accept a job offer, get married. You know, there are many different things it could represent. Okay, and then we'll look at how you can model these in a latent variable framework. And usually we assume kind of a random utility structure where the person chooses the option that gives them the highest payoff. And these are different types of questions you might be interested in when you do this. So, well, actually, these are different variables that could affect your decision. So it could be your past choices could matter. So it turns out for a dynamic model, your past choices have to influence your future choices for a model to be dynamic. Or you could just have some other x's that matter, that may not actually be choice variables. Like, for example, your age. You know, you're not choosing your age, but your age could be important for your decision making. Or the local unemployment rate. Like, that changes over time, but it's not a matter of choice. And then all of these models, we're going to try to incorporate unobservables, because we have to explain why two people that are observably similar make different choices. You know, so we can't assume we see everything that's relevant to their choice, so it'll be important, like how we introduce unobservables as well, right? So the x's we observe, the d's we observe, and then the epsilons would be something we don't see, but that might still be important for their decisions. Okay, so here's like a decision model. You choose option 1, you know, and this, we'll look at an example with utility, but this is usually the utility of option 1 exceeds the utility of option 0. Okay, and almost all like binary choice type models you can put within this framework. Both, it'll either dynamic or static, so we'll start with some static models. Okay, and a dynamic model means that your past choices affect the future. So when you're deciding today, like, I'll show you an example, like if I work today, that increases my work experience, and that'll give me a higher wage tomorrow. You know, so that's like a dynamic consideration. You know, that my choice today isn't just my wage today, it's also what my wage will be tomorrow. Okay, and why might we estimate these types of models? So you might want to know, you know, if I change something, how does that affect D? So if I change, say, the price of, you could have used public transportation or use private transportation, like a car or public transportation, you know, and I change the price. And I want to see how does that affect demand for public transportation, or change the price of gasoline or something. So, yeah, or you may want to say if you change lag choices, how would that affect future choices? Or it might be something totally different. So I'll give you some different examples of different types of policies that we could analyze with this model. Okay, so here's an example. So this is the utility that you could say it's like a couple deciding, but it's really a female labor supply. So we're assuming the man works and the woman is deciding whether to work or not. I mean, nowadays actually labor supply for men has fallen a lot in the US, and for women it's gone up. So, but traditionally people kind of assume that all the men want to work, and for women, because of children and things, they are deciding whether to work or not. So C is consumption. D is whether she works. So if she doesn't work, then this, I mean, you could call it leisure. Labor economists call it leisure, but it's really like staying at home and doing home production. Kappa are just whatever factors influence her utility from not working. So if she has children, for example, that could be in kappa. And then epsilon would be unobservables. So that would be like an unobserved preference for staying home. Okay, so that's, and then we could put a functional form. Later on in the slide, I'll put a functional form, okay? And so we'd assume the usual properties that, you know, more consumption is better, but there's usually diminishing marginal utility of consumption, that you prefer leisure, you know, for the same level of consumption. So, okay, in kappa, you can put whatever you want in kappa, but, you know, number of children would be a crucial thing that might affect her willingness to work. Okay. So then on top of this, it's usually maximize utility subject to some constraints, right? So this would be the constraint that consumption, so Y is the income of the family, which could be like the husband's income, plus any non-labor income. Plus, if the wife works, so if D equals 1, then you get the wife's wage, right? But if she has children, so N equals 1 means she has children, then she has to pay a child care cost, pi. And so we're going to look in this model at how you could evaluate the effects of a change in the child care subsidy. And this is actually very relevant for Russia, because I read a study where they were looking at, I guess during the Soviet times, childcare was almost free, you know, and so most women worked and they didn't have to pay a lot of money to put their children in childcare. But then with this transition, apparently the cost of childcare has gone way up compared to what it was before. You know, so now I saw a World Bank study actually using Russian data where they were analyzing how changes in the price of childcare affected female labor supply, like using, you know, kind of a similar type of model. Okay, so the idea is you maximize utility subject to this constraint, and you may or may not have data on pi. You know, like it could be that pi is totally unobserved. And the policy we're interested in, we might want to like change the level of pi. Like if the government introduces a child care subsidy, what effect would that have? Okay. So within this type of model, because you don't see wages for non-workers, we normally also would introduce what's called a wage offer equation. Because you want to try to model, well, what would the wage be for people who are not observed to be working? Because even though they have 0, you see 0 for them, but that's not really their earnings ability. Like if they would choose to work, they would make something higher than 0, right? So this is a wage offer equation. And Z would usually have like education, potential work experience, and this would be another unobserved factor determining wages. So there are two unobservables, like epsilon, here, that's the unobserved preference for leisure, and this is the unobserved factor affecting wages. Okay. And the reason we need this unobservable is we're going to have people in our data that have the same Z's. The Z we observe. They have the same Z, but in the data they have different wages. You know, so you have to have, because in the end we're going to estimate the parameters using maximum likelihood, and you have to be able to explain why people who observably look the same make different choices. So your model has to allow for that. So if you have different wages, but you have the same Z's, then there must be some unobserved factors affecting wages.
Excuse me. Don't we expect that mu IT are serially correlated?
They could be. Yeah, but right now it's just static. Yeah, but when we do dynamic models, they could be serially correlated, yeah. Yeah, and also the epsilon and the mu could be correlated. So, and correlated over time, yeah. Okay, so if you substitute in the constraint for consumption, then you get, this is the utility if the wife works. So then she has the Y and she has her own wage, but she incurs a child care cost. And she has less of, you know, leisure, or she doesn't stay home. And then this is the utility if she doesn't work. And she's comparing those two options. So that's how we get like that binary choice. They call it a threshold crossing model. Like is U1 bigger than U0, then you choose D equals 1. Okay. And so this is the index. So this V is really the difference between U1 and U0. And so whether that's positive or negative determines whether you work or not. Okay. And that's like a typical framework for modeling binary choices. I mean, this is also used in marketing. You know, do I buy this brand of pizza or this other brand of pizza? You know, so from this you can get like a logit model, probit model. So if you assume the errors are widely distributed, you can get a logit model. If you assume they're normal, you get a probit model. You know, and then you can extend it to 3. I actually teach all this because I teach the econometrics. So. But this is the basis for, you know, many different types of models. Okay, so we would call all the variables that determine the choices the state space. Okay, but we may not see all of the state space. So we're assuming the individual sees everything. So they see their shocks. These are preference shocks and weight shocks. But the researcher in our data set, we may only have these observable elements. You know, so usually we try to build in the fact that there are many things we don't see, right? That affect wages, that affect preferences. Okay, so this omega with a minus is going to be the observed state space, and this is the total state space. Okay, and this S omega minus, these are all of the unobservables that would induce somebody to work. You know, so there are going to be a whole range of values of the unobservables that, given the observed state space, would induce someone to choose one. Okay? So the reason for writing this, I'm going to show you like the likelihood that you would use then if you want to estimate these model parameters. Is it clear, the notation?
A small here means how you control the region specific effect. Let's say that if like particular individual or household you want to like verify is it in rural or urban area, means how you control for the region effect here.
You could put, like if you had in your data rural or urban, and that probably affects their wage offer,
Yeah.
you would just put it in the wage equation. And that could actually be something that affected wages, but maybe not preferences. Like you have to decide where it belongs. But yeah, if you have, the more data you have, usually the better you can control for things. I mean, I just put like a few things, you know, but ideally you'd want to put everything that you thought was relevant. Or it could even, like what region they live in, that could all go in the wage equation. Yeah. Okay, so the probability that somebody chooses to work, given the observed state space, is going to be this integral. This is just saying the area under all those unobservables that lead to the working decision. Okay, so this is like the set of unobservables that would induce you to work. Okay. And so that I'm just calling G, and then the probability that you don't work is just going to be 1 minus that. Right? So if I estimate, let's say I estimate a probit model, just do you work or not, where I regress it on a lot of things, right? This is what I'm trying to recover. When I do that estimation, I'm getting G. Okay. Because I want to compare like some different estimation approaches, because that would be a simple thing that you might do, just a probit model for do you work or not. If I do that, I'm not going to recover U, or you know. So there are different approaches. Like if I have these data, and actually, you know, they're kind of different schools of thought even for how you do policy evaluation. And in the U.S., some universities, you know, most of the people do what's called like non-structural estimation versus structural. Like, do you hear these terms sometimes, like structural versus non-structural? So structural estimation, you're usually concerned with recovering these are called structural elements of the model. The utility function, the wage function, this F is the cumulative density function of the unobservables. That's like all the different elements of the model. The model that I had was just maximize utilities subject to the constraint. I mean, it was a simple model, right? But if I can solve that model, if I know the parameters and you know, those are the structural elements. So structural estimation would actually try to uncover these things. Non-structural estimation, usually you're just uncovering G here. And G is kind of a function of all those other things. So you're not trying to separate out the different things, right? And then whether or not you're parametric or non-parametric, you know, so that's kind of a functional form question. You know, do I assume a functional form or do I try to do something like non-parametrically? So, I mean, I guess like neural networks is one non-parametric approach, or you could do like non-parametric regressions or something semi-parametric, which is kind of in between. So that could be for either approach. But actually, to be honest, most structural estimation is parametric because it's pretty difficult to do this non-parametric. And then non-structural, sometimes people do it non-parametric, but I would say most times people just do probit or logit, so even that is usually parametric. Okay, but the question of whether you have structure or not is really whether you're trying to uncover the utility function and, you know, separate out those different elements. Okay, so let's look at some examples of why would we want to uncover these things? Like, why isn't G enough? So it turns out sometimes G is enough, like for certain questions, but then for other questions, it may be necessary to actually uncover U from the constraint so that you can vary the constraint. Okay. So if I just wanted to test, like, does something increase the probability of working? Okay. Something that I observed, like let's say I would say, well, let's see, I have some examples, we'll see. Like if I just say, if I increase some variable in the state space, how does it affect the participation probability? For those types of questions, G is usually enough, actually. But then I want to show you like this other policy, like what if I change the child care subsidy? And in my data, I don't have that change. You know, so this is like a hypothetical program I'd like to evaluate that I don't have in my data. So for this, you actually need to have the structure of the model to be able to do this. So whether you need structure or not, you know, there's a big debate, should I do structural or not structural? And I think it's not, it's more like for this question that I'm interested in, do I need to be structural or not? So certain questions you can answer without having the whole model, whereas other questions you couldn't answer at all unless you actually did a structural estimation. So actually, when I teach these like policy evaluation, we spend about half the class on non-structural and half the class on structural. You know, because I think you need to have both to be able to know what's the best method given my question.
Excuse me. So if goal is to answer the first two questions, you don't need structural.
Yeah, usually you don't need, for a lot of questions you wouldn't even need to. Because usually to do structural estimation you have to make more modeling assumptions, you know, and then people might disagree with those assumptions. You know, so you might be better off doing like more of a non-parametric estimation than do non-structural, like if you can. Okay. So this is just how we could, you know, meet some of these goals. Like if we just want, because, you know, empirical work has different goals sometimes. Like maybe you just want to test a model. So you could say one implication of the model is that the probability of working increases in the wage offer, right? So I want to test that implication. Well, to do that, I just need to have some variable that only increases the wage offer, okay? So to test that, does the probability of working increase in the wage offer? I need to have something that's only in Z. Okay, because that's going to only vary wages, so I can hold everything else constant. So let's see, what could only be in Z? Like we had a variable, how close you live to a city, because that affected wage offers. In Mexico, I had data from Mexico, and it turned out there were a lot more factories and things close to the city, so that was a good variable that affects wage offers. Or maybe your potential experience affects your wage offer. You do not want it to appear in kappa, because that would be a problem, because then whenever you would change that variable, it wouldn't only affect your wage offer, it would also affect your preferences. So something that affects your wage offer but doesn't enter anywhere else in the model is called an exclusion restriction.
What about this labor market institutions? Labor market institutions, those matters here as well.
Yeah, it could affect the wage offer only, that there's some regulation that affects your wages, but it doesn't affect your utility from working. Yeah. So these exclusion restrictions are pretty important sometimes in these models, that you need some variables that enter only in one part of the model and not in a different part. Okay. And I mean, you can't usually test this implication directly because you don't see wages for everybody. So that's why we need something in Z. If we saw wages for everybody, then you could just, stick in the wage. But for non-workers, you don't usually see wages. Okay, so if I had G, which I could estimate parametrically or non-parametrically, so the only limitation, if I do it non-parametrically, usually that restricts you that you can only do extrapolation within the range of your data. Whereas a parametric model, you can usually extrapolate outside the range of your data. I mean, whether it's a good idea or not to do that is another question, but a limitation of non-parametric is you can just extrapolate within the range of your data. Okay, so you could not, with a non-structural approach, estimate the effect of changing pi, actually. Because if I change pi, well, first of all, I'm assuming we don't see pi at all. Okay, so I'm assuming that we would evaluate the effect of a child care subsidy, and in our data, there's no subsidy at all. Okay, and so therefore, you can't really just take some derivative because you don't even see it in the model. And you couldn't just look also at, you can see how the probability of working varies with n, because that you can see in your data. You can see women with different numbers of children, but we don't see anywhere a variation with pi. Okay. And the difference for non-structural parametric, you would just assume like that the errors are normal or wiable and just do logit or probit. So that's the only difference. And the only benefit is you can maybe extrapolate. You can accommodate more variables, because with purely non-parametric regression, you have cursive dimensionality and things comes in. So with parametric, it's maybe easier to do.
Excuse me. Why logit and probit is non-structural, while the parameters that we estimate in logit and probit, there are some structural parameters.
No, they're not structural. They're parametric. So logit and probit would be parametric. So the definition of parametric has a finite number of parameters.
Okay.
Yeah, so like a probit model, you just have the mean parameter and the variance parameter. And then if you have some x's, you have the betas on that. But you don't uncover the structure of the model, like the utility function.
But the betas that are parameters that we estimate, for example, we have education, some bunch of observables, the parameters that we estimate, are they structural parameters?
They're not structural, but they're functions of structural parameters.
Okay.
So that's actually reduced form.
It's reduced form.
Yeah.
logit probe it.
But the thing is, if you never wrote down the structure, usually you don't even know what functions they are. But ultimately, they are functions somehow of the structural parameters. That's why people call these methods reduced form methods. Because reduced form is actually where you have to recover functions of structural parameters. But it's a little funny to call it. I don't call it reduced form because if you never write down the original structure, then how do you know it's a reduced form of what? You know, like originally when they introduced that sort of naming, people were talking about here's the model and here's my reduced form, which is a function of that model. But nowadays people use that very loosely, and they call everything reduced form, even when there's no model. You know, so that's why I prefer to call non-structural and only reduced form when there's actually a model. You know, but that's kind of different from how other people use it. Okay, so let's look. So I'm going to non-parametric structural. Usually it's not feasible because it's, and I have one paper where we try to do this with some very simple examples, but I could tell you about it like if you're interested. But usually people would use parametric methods. So now I'll show you how you can evaluate the child care subsidy even if you don't have any data on the subsidy. Okay, it sounds like too good to be true, kind of, but okay, so this is writing down an actual functional form. So your utility is consumption, and this is your utility from not working. And we can parameterize that as, you know, function of kappa. So that would be like number of children, whatever you want to put in here. Maybe education of the woman might affect her utility from working. And then this is the unobservable. This is the budget constraint. Her consumption is, say, husband's income, wife's wage that she only gets if she works, and then subtracting the child care subsidy. And then this is the wage offer equation. And to complete the parametric model, you have to make some functional form assumption on the errors. You know, and so this is assuming it's joint normally distributed. You can make different assumptions, but most commonly people would like bivariate normal. Okay, so they could be correlated. So there's some covariance. Okay, so this is the threshold crossing utility, so comparison of utility 1 and utility 0, and you see that y actually drops out. So in this model, because it's a simple linear model, husband's income ends up not mattering. Because you get your husband's income if you work, and you also get it if you don't work. So if you have linear consumption, you know, it actually ends up dropping out. But if you had assumed a different functional form, it might still be there. Because in this model, the utility of leisure does not depend on the level of consumption. You know, like, you could make it slightly more complicated. Like how much you enjoy leisure might also depend on your consumption. But that's why there's no y there. Okay, and this is the threshold crossing model here. Okay, we don't have to have additive error structure. Like this example is just simple because we just have this be additive. Because if you do labor economics, you probably were thinking, why doesn't she have log wages instead of wages? Because usually you have log wages are linear and not wages are linear. Okay, so I did wages just so it would be additive to make it simpler, but I'll show you later you can estimate these models even with when the errors don't appear in an additive way. Okay, and so now usually we get the parameters using either maximum likelihood or simulated method of moments. I prefer maximum likelihood because maximum likelihood uses all the information in the data. So I think if you can do maximum likelihood, it's usually the better method. But there are some cases where, especially if you have missing data, where it's much easier to do simulated method moments. But like, actually Heckman has a paper comparing, and he finds that simulated method moments is a little more arbitrary because you get to pick whatever moments you want to use, you know, and it's harder to know if you've got good moments or not. Whereas they're equivalent if you choose the first order condition of the likelihood as your moment, then the method would be the same. Okay. But I usually encourage my students to do maximum likelihood if they're able to, because it's more efficient and it's less arbitrary. But so if the woman works, you see her wage. So you've got the probability she chooses to work. So this is the joint probability that she works and that her wage takes this value. And if she doesn't work, you only know she doesn't work. So you only have the probability she doesn't work. You know, so you have more information if she works than you have the wage. Okay, so the likelihood has these two parts. Okay, and these are all the parameters of the model. Okay, and I'm assuming we don't see childcare costs, so that would be a parameter. So this was in the wage equation, the coefficient on Z. This was the coefficient on kappa. Kappa and N. N is the number of kids she had. Okay, and then these are the elements of the variance covariance matrix. Okay, so let's see. So if I don't have any data on pi, like assume if I didn't have any data on pi, then pi actually enters together with beta n in the model. So what you'd estimate from the model is just this combination beta n plus pi. Okay. These variance parameters, I won't go through in detail the argument how they're identified, but if anybody knows like the Heckman two-step estimator, which they teach a lot of times in like econometrics class, or it's where you do the wage equation and you have a model for do you work or not, and you put in the Mills ratio correction. That would be used to get the wage parameters. And then if I only did the Probit model, do I work or do I not work? That's how I would get, so the Z and kappa appear in the wage, in the working and not working. So from only that Probit information, do I work or not, I get this gamma over this, well, the sigma psi is kind of important. So let me, let's see. Sigma psi, where did I find it? Well, these are the different elements. So if I write down the probability of working, oh, here it is. Sorry, I should have highlighted this. See, if I write down do you work or not, it's just a probability that this is greater than 0 and this is less than 0. So if I make these normal, because I'm assuming they're bivariate normals, so the difference between two normals is normal. So that's how you get the Probit model. Okay, so sigma psi is the difference between these two things. And just using the information on do you work or not here, I can get these two things separately, but only if they're variables in Z that don't appear in kappa and variables in kappa that don't appear in Z. Like I need to have some exclusion restriction. So, and the reason is, well, actually what I need is a variable in Z that's not in kappa. So why is that? Well, from the wage equation, I can get this gamma, okay? And then from the Probit model, I can get gamma over psi, or sigma psi, okay? That allows me to get the sigma psi, putting together those two pieces. But if everything would overlap, if all the Z's and the kappas were all the same thing, then from the Probit model, I would only get gamma minus beta over sigma psi. You know, and then I would not be able to back out sigma psi by itself. Okay, so let's look at like why would we be interested in sigma psi by itself? But I don't know, is the idea clear? Like from the wage equation, because I see wages for workers. Okay, and that lets me get gamma. I mean, this is identification, like Steve Durloff was talking about, like how do you identify things. But from the wage equation, I can identify gamma. From the work decision, like do I work or not, I get gamma over sigma psi.
So on the first stage, on the first step, we need to estimate the wage equation, right?
Yeah, we actually don't need to estimate. We can do everything all in one step. Like, I'm just saying it that way in 2 steps just for the identification argument. But when we would actually implement this, I wouldn't actually do a Heckman 2-step correction or whatever. I would actually just program this directly.
And
Yeah.
should we make an assumption on the amount of, on the share of agreements that we want to stay broken on the
Yeah, we're not assuming, we're assuming we have data. So we see the women. Yeah, I'm assuming we have microdata. So I see a bunch of women, like 1,000 women. I see their characteristics. I see how many kids they have. I see if they're working or not. You know, I don't see their wages. I only see the wages for the ones who choose to work.
how can we apply this approach to ex ante regulation?
Yeah, that's what I'm trying to, like, because I'm assuming that we don't see a child care subsidy. But let's say I'm the government and I want to know, well, if I would put a child care subsidy, how would that affect working behavior? So I'm assuming that I can estimate this model without any subsidy in the data.
So currently we have some division on these 2 groups, those who are working and those who are not working. And
Right.
what will be with this division after the introduction of the law, right?
Yes, yes, and then we're going to see how many people, after we introduce the program, will now choose to work. And that'll tell us about, like, how many people take the subsidy, what will the program cost the government, how should I design the subsidy if I want to induce so many people to work? Yeah. But for right now, I'm assuming in my data set, nobody has the subsidy. So I'm just estimating this is a female labor supply model. Yeah.
Excuse me. Once you want to estimate this static model, you write this likelihood function and write the maximum likelihood program and estimate 6 parameters for this one.
Right.
Do you estimate all 6 parameters at the same time?
Yeah. Yeah, from the likelihood equation, you estimate all 6 parameters.
So it's a 6-dimensional optimization
You search
problem.
over 6 parameters, yeah.
So my question is, once you extend the model, you have richer model, dynamic model, there's gonna be
More parameters.
more parameters.
Well, I mean, I even have models that have 100 parameters, so like,
So 100-dimensional optimization, you solve 100-dimension?
yeah, I mean, they're not, it doesn't sound, I mean, it's not as crazy as you think because a lot of the parameters are kind of pinned down. Like the wages, you see the wage, you know, so you can start with good starting values from a wage regression. You know, so a lot of the parameters, they enter in very restricted ways. So they're not like completely free that they could be anything, you know. So usually if I would estimate this model, I would run a wage regression, get some starting values, you know, and then, yeah, but some of these models, they're not concave a lot of times. So you actually have to search a lot and use a good algorithm for optimization. But with 6, it's pretty easy to do. But then when you have very complicated models, they can actually, you know.
Do you use a combination of calibrating some parameters and estimating some other parameters?
Yeah, definitely. I don't do that too often, but in the dynamic models, there's a discount factor. Sometimes, if you don't have a long panel, it's very hard to estimate. You might just have to pin it down. Yeah, but it's similar to what macro guys do. So, I mean, a lot of in macroeconomics, there's a whole school in macro where they start with micro foundations and then they build up. And their models are actually very similar to this, but they don't worry as much about estimation, and so they're more willing to calibrate sometimes. But they worry about other things like general equilibrium or multiple equilibria, you know. But it's actually macro and micro are pretty similar when it comes to doing this kind of work. It's just microeconomists worry a lot about how you estimate it, like with maximum likelihood, because we try to fit the micro data. Whereas macroeconomists sometimes try to fit, they do method of moments, and they don't try to fit the micro, like each individual observation. Okay. So the estimation is different. But So let's look now how we can do this policy, okay? But so you have some variables that are only in Z, so those affect wages, but nothing else. We might have some variables that are only in kappa that affect the value of leisure or staying home. And then you have some variables that affect both. Like maybe education affects your wage offer, but it might also affect your preferences, you know. So those are 3 types of variables. Okay, so now let's look, you know, so the first 2 goals you could pretty easily vary Z. Well, let's look at the 3rd goal was the hardest one. That was the one where we changed the subsidy amount. So here's how I can use this model to do the subsidy. So if I introduce a subsidy, that changes the budget constraint, right? So now, if the wife works, she gets W, but instead of paying pi, she now pays pi minus tau, okay, where tau is the subsidy. So let's say childcare, maybe it costs 300, well, it's hard for me to think in rubles, but so I'll just like $300, say. And then if she got a subsidy, maybe of $100, then childcare would just cost $200, right? But she only gets the subsidy if she works. Okay, so this is with the subsidy. So tau equals 0 would be no subsidy. And so now the probability that she chooses to work, you know, given her state space, so that's her characteristics, and given the subsidy, will now be this. This is, when I compare the U1 and the U0, this is the V, the difference between the 2. So if she works, she gets this wages, but she loses this utility, but she pays this subsidy. Okay, so she's losing this, but if she has a subsidy, then it doesn't cost as much, right? So to evaluate a subsidy, you can see it's kind of crucial. You have to have this parameter. Okay, but if I estimate the other model, and I got all these parameters, so I estimated the other model even with no subsidy. And I got gamma, I got beta, and with one exclusion restriction, so one variable that affects wages that doesn't affect preferences, then I'm able to get the sigma psi. And if I have all these ingredients, and this beta n is just the coefficient on children, so I would have that for my estimation, then I can actually simulate. So with no subsidy, this is just 0. So I can actually vary tau. I could, like, you know, have the subsidy range from 0 up until, you know, whatever subsidy I wanted to try, and then I could see how many women will choose to work under different values of the subsidy. And the reason I'm able to do that, the reason is because the subsidy is similar to a change in the wage. You know, because if a woman now, that provides the variation in the data that lets you identify a subsidy, because it's kind of like a tax on your wage. Because every time you choose to work, you now have to pay childcare. You know, so it's analogous to you make a lower wage. You know, like a woman who makes $1,000 and pays $100 childcare is similar to a woman who makes $900 and pays $0 childcare. You know, so you're basically using the variation in the wage to identify the subsidy. Okay, so that's how you can, like, use some variation. So even if our data has no subsidy information at all, we can still extrapolate, like, using the other sources of variation. Okay, but the exclusion restriction is important because we have to get the sigma phi. You know, but then you could tell the government, like if the government asks you to do the study, you could say, well, I predict so many people are going to take up the subsidy, this program will cost you this much money. You know, if you want to induce a 10% increase in women's labor supply, the subsidy has to be at least this big. You know, so you can answer all those types of questions. So obviously we made more assumptions, because you put down the structure of your model, but you're able to answer a lot of different questions, that you otherwise couldn't answer. So I think that's kind of the power of these types of models, is you can answer a lot of different questions, but the trade-off is you have to make more assumptions about the structure of the model. Okay. So the critical thing, you did have to have an exclusion restriction. So a lot of times in these models, you need to be able to have one part of the model move, without the other part moving. Okay. And it's kind of like a tax on the wages. So there's policy relevant variation, even if you don't have direct variation in subsidies in your data set. Okay, so there's not very much work on nonparametric structural estimation. I have one paper, but it looks like, the applications, it only works in special cases, what we're doing at least. So this is an area that's kind of unexplored, I would say, like doing more non-parametric structural work. Okay, so now, so when is our break, Valerie? Like in 10 minutes? Okay, all right. Well, let me just start a little bit to talk, because I wanted to motivate now dynamic models, because you can actually see a dynamic model as an extension of the static models. I think sometimes people think they're so much more complicated, because now you're not just modeling one decision, now you're modeling decisions over time. And you might think that that's a huge complication, but you can actually view them as an extension of the static framework. It's not as big a complication as you might think. So I just wanted to tell you a little bit how you would go about estimating a dynamic model, like what methods, because that's something that's really recently been developed, all these new methods, and that kind of pushes the frontier. The only thing, a lot of these methods are not available in Stata or something. I think that's kind of a barrier, because usually you have to program up this model, so you have to use, there are many programs available. You can use MATLAB, or I use R sometimes, or I use Fortran, C, Python, Julia, I guess, is the latest language that has anybody tried Julia? Yeah, I guess it's starting to be popular, right? MIT, I think they...
Quantic, Sargent, and...
they're using Julia?
Julia and Python.
They have a web page, right?
Yeah, I think I'm too old. I don't know if I can learn another
They are
program.
more macro.
They're more macro?
The Quantic, they have a website, Quanticon, the Sargent and one of his co-authors.
Well, Sargent's older than me, so he's learning Julia. But so there are a lot of different languages you could use, but Stata is like, I don't think you can, it has some sort of programming language, but I think it would be too difficult to try to do something like this within Stata. So I think the biggest barrier to these methods is more programming, that you have to program your model. Okay, so there are different ways to introduce dynamics. The simple way I was going to put it, so it's a dynamic model if your choice today affects your utility tomorrow. That's what makes it dynamic. Okay, so the way this is going to do it is if you work today, you increase your work experience, and that affects your wage offer tomorrow. Okay, that's going to introduce some dynamics. Okay, and so then we need to have just a law of motion for how experience evolves. So this is saying every period you work, I increase my experience by 1 year. You have to decide on the time period, but usually people do annually, or if they're modeling like job search, it might be quarterly, or if you model fertility, it may be every 2 years. So you have to decide what period. Well, you could have continuous time models too. Most of what I do is discrete time models, because the data sets a lot of times refer to a year. Okay, so now we have a true time period that we get a shock every time period. So first I'm going to assume they're independent. So IID shocks. But in reality, weight shocks are pretty correlated. So we'll allow later on I'll show you how you can introduce some dependence in these types of models. Okay. So now we're going to assume that when you decide today on something, you're not just maximizing today's utility, you're maximizing the expected present discounted value of remaining lifetime utility. Okay? And we'll assume that it's finite horizon. Most of the models I estimate are finite horizon. I mean, people die anyway, so life is finite. So if you don't have intergenerational, there is some finite. Because some of my models I have like age 90 or something in the last period. But here, because we're not going to model retirement or something, we'll just assume the last period is like period T, like maybe when she retires. Okay, so this is now every time period I'm deciding on D, and so this is in time period T. I'm maximizing, I always have these two options, but I'm only deciding period T in this equation. And the future matters because if I work today, I increase my experience in all future time periods. So I'll have a higher wage offer in the future. And this is the expectation of the future utility conditional on the state space. All right. Okay, and usually the way we solve these models, well, that's called the value function. So this thing here is called the value function, which, I mean, this is used a lot also in macroeconomics. And actually, I found out my dad, because I asked him what he did for his master's thesis, and he got a physics master's in physics. And then he said I estimated a Bellman equation using Petra, and I'm like, that's what I do, So I'm doing exactly what my dad said, like in the 1960s, when they were still using punch cards and everything. So I guess these methods are used also outside of economics, I think originally in other fields. But the way we use them here, you can write the value function as current, so this is current period value function. This is the value if I choose option K, which is 0 or 1. Okay, I'm just choosing, do I work or not? This is utility today, and this is the expected future utility. And this model only introduces one additional parameter. So the difference between the static model and dynamic model is only this delta. That's the only additional parameter. So now instead of 6 parameters, I have 7, actually. And that's the discount factor, because you assume that you discount future utility. Okay? And then in the last period, if it's a finite horizon model, then you only have current period utility. If it's an infinite horizon model, you normally have to solve a fixed point. So some people estimate infinite horizon versions of these models. These are also used in like macro and the intergeneration, or like you could have different generations making decisions that affect the future generations. So some contexts, it makes more sense to have infinite horizon. And you could also have multiple agent models. Like I do mainly single agent finite horizon where I have a lot of decisions. But some people estimate like multiple agents, infinite horizon. Okay, and the expectation is taken over everything that you don't know. So that's the distribution of all the future random components. So this expectation is really an integral over, all the future shocks. All right, and if we just put in what our model was, this was the difference. So this is the Bellman equation, and you'd be comparing 0 and 1, like the same as in the binary model. And I can write this as a threshold crossing model, the same as I did for the binary case. So now this is what we had before, But now we pick up this additional term, because I also, if I work today, I get a benefit in terms of having higher expected value, or the value function is going to be higher in the future. Okay, so the difference between the static model and the dynamic model is like this term in brackets. So that's your future utility, right? So this is my present utility of working, and this is going to be like the fact that it increases my future wages. Okay. So now the complication in these models is I have to actually now get these terms. But if I can get these terms, the value functions, then I can just do it with maximum likelihood and everything the way that you do for the binary. Okay. I guess we can take a break, and then after the break, I wanted to tell you a little more like how would I get those terms, like how do I estimate these models, and then go into some information about how you would apply these models, and then hopefully we have a little time to talk about how you use this in like more complicated frameworks, like not just binary models. Okay, so the state space in the next time period is going to be completely determined by the state space in this time period, and then what other choice you make. Okay, so that's just one thing to notice. And to solve this, to write down, say, a likelihood equation, I need to know these expected value functions. Right? We call these like Emacs. They were the maximization between these two things. And it's really the expectation of this, so we call it the Emacs usually. So you need to know what these two functions are. Okay. And so a full solution for the dynamic programming problem would include having to find these Emaxes. And then once you have them, then you can write down the likelihood equation. Okay, so if you have a finite horizon model, then you normally solve this by backwards recursion. And the reason we start with last period is because there's no future. So in the last period, you only have the current period utility, so you don't need any roots, right? In the very last period, it's just the utility function. So now just to keep things a little simpler, we'll just assume that these z's are not changing. Otherwise you need to have some law of motion for like how the z's are changing. So for example, fertility, usually I would also have a model where fertility is a choice. You could have female labor supply as a choice and also fertility a choice. But we'll just assume maybe that the woman is old enough that she's not still having kids. So that these things are, the only choice is work or not work. Okay, and if you have a current number of children, you may also have the ages of the children might be in your state space. Like maybe she would work if her child is 12 years old, but not if they're 6 years old. So that could be in the state space. So under normality, so to get this Emacs, so if you write out what it is, you'll get these expressions. So this is like the expectation of the error term given, this is coming from here. Given that you work and given that you don't work. Let's see, which is that's the equation. There was one where, that's the static model, right? Well, you get the difference in the two errors. I guess it is the same as the static. It's way back here. See here, you get the difference in these errors. But now you have the expectation of the difference. So that's why you actually have the expectation given that you work and the expectation given that you don't work. So, because they're normally distributed, we actually have closed form expressions for those expectations. So, actually a more complicated model, you don't usually have closed form, so you usually do not have to derive these things. Like, it's usually done with simulation methods, but for the normal distribution, you actually have a closed form expression. So if you write out what these Emaxes are, like this is the Emax t. So this is, so for t minus 1, you need the Emax t, right? And this is actually the expression, there's a closed form for it. Okay, but actually, if I estimate a more complicated model, usually you're not able to get closed forms, so you don't have to worry too much about like how you derive this, because usually you wouldn't have to, because your model would be too complicated to get this. But just for the simple normal, like Ken Wolpen had a model that was just binary decisions with normality, and he actually derived out all these expressions. Okay, so it's a normal CDF, that's the only integration. And then here's a t minus 1, the value function. You've got the current utility plus this discount factor times the Emax. And this, so if you work, the next period your state space will be different because you'll have more work experience. You know, so you have to find the Emax at each possible state space element. So that's part of the solving these dynamic programming problems. You have to get the Emaxes at all the different possible state space elements. Okay. And then this is going to be this, you know, the index that determines if that's bigger than 0 or less than 0, whether you work or not. I mean, in this model, y also just drops out because of the additivity. And then, so here's the Emax. So you need all the different Emaxes. So in period t, you have an Emax. Then you go back, you have period t minus 1, you have an Emax. So usually the way you solve these models is there are 2 steps. In the first step, you start the last period, and all you do is get all the Emaxes. That's called solving the dynamic programming problem, that you only get all the Emaxes. Then once you have those Emaxes, then you can write the likelihood. Okay? And we do this iteratively, so I think I have a slide that goes, you know, but so the first step would be get all the Emaxes. So this would be now in period t minus 2, the current utility, and then you need the t minus 1 Emax. You know, and you would solve this all the way back to period, the first time period. Okay. So continue solving all the way back to the beginning. And once you have all the Emaxes, then you have all the information necessary to calculate these cutoffs, and those are the things that are crucial to get the likelihood function. So this omega, that's everything you observe, the observed characteristics about the woman, and then you can write down the probability of working and not working. Once you have the Emaxes, you can do the likelihood. Okay, so it's kind of the 2 pieces. And you're usually, when you do maximum likelihood, you're iterating over parameters. So you have some initial guess. You start with a guess, right? Usually you want to have a smart guess, so I would like do a regression, wage regression, those would be my initial guess. And maybe look at some other papers, get some idea of what might be reasonable parameters. Solve the Emaxes, get the likelihood, and then your optimization algorithm would take you to a new set of parameters. So then there are a variety of choices. You know, you could do like usually these problems are not differentiable. So I usually use something that's kind of similar to simplex method. You know, because a lot of the optimizers assume you have derivatives. And with all the discreteness, they're not like horribly non-differentiable, but usually I use non-derivative methods for optimizing validation. They're pretty smooth, but technically they're not differentiable. Okay. So the researcher, we now need to have data on H. And so I'm going to assume I have some data. Well, you do not need to have data over the whole person's lifetime. Okay, so my model is about the whole person's lifetime. They're, you know, from maybe when they get married to when they retire. Okay? But in reality, I'll never have data that covers the whole lifetime, right? I usually just maybe see people 3 or 4 years if I have a panel, short panel. That's okay. So your data does not have to cover all the periods of your model. Like your model could be over the whole lifetime, even if your data is only for a few years. Okay. So some people think, to estimate dynamic model, you need all these data requirements. It's not really true, because you can just write the likelihood for the years that you see them. Okay. A lot of times you need more than one period, though, because these models are hard to estimate, like the discount factor and everything. If you only had a cross-section, usually you cannot estimate this. You need at least a short panel to do dynamic models, like at least 2 time periods. That would be the shortest panel you can get with it. Okay, so assume we start seeing people.
Excuse me, if we have cross-section, but for 2 time or 3 time periods, not panel,
Yeah.
can we estimate this? Just moments, maybe.
Well, sometimes if you have cross-section data and they ask you in the data about historical things, like did you work last year, things like that, you can kind of convert it into a form that it would fit. But like if you only know do you work today and you didn't have work experience, then you couldn't do this. But if they said how many years in the past have you worked and are you working today, you might be able to do it. Yeah.
If you have multiple cross sections, can we use the moments? Definitely we can't use maximum likelihood because, but can we use
So you
SMM?
you need all the elements of the state space. So as long as you have those, but they usually relate to last period. Number of children today, work experience is a crucial one in this model. As long as you have the state space, you can use any sort of data. So you might have a cross-section where they ask you a little bit historical information. You have to be a little creative to get your data to fit the model. And so this would be the first period you see them, and this the last period. And that could be different. Like some people you may see at age 20, other people might be age 40. If you had a random sample, you'd see people at different ages. So that's fine, actually. There's nothing that they all have to be the same age. So it need not be, if the model begins when people get married or something, it doesn't have to be the first period. Okay, this would be the likelihood. So the likelihood is the same as for the binary case.
And with the cross-sectional analysis in both the time points, if the unit of analysis, let's say household, if it is different, can you make this thing? Like the unit of analysis will be different, but it will be representative sample in 2 time points.
Well, as long as you could do this, could be a household model. In fact, I estimate household models where I have a husband and wife, and there's like weights on the husband's utility and the wife's utility.
Yeah, I'm talking in both the points, like the persons are not the same, they are different. Oh, like in the cross-sectional data, let's say in 2 time
repeated
points.
cross-section.
Cross-sectional data 2 time points, but the unit of analysis are not same. Like it's not the same household, which has been surveyed in the net.
Yeah, normally it doesn't work unless you have you just have to be able to have information to get the state space. It'll depend on what questions were asked in the survey, if you have everything in the state space. So it doesn't have to be a panel, Although if you want it later, hopefully I'll talk to you a little bit about unobserved heterogeneity, because for those methods you actually need to have more than 1 time period usually. But you might be able to do it with cross-section data if you have everything that's in the same data. So the likelihood actually is the same. The only difference is now when I write down this probability, I have that difference in the future Emaxes. So there's like one additional term, That's why I have to actually first get all those Emaxes, and then I can write down the probability and do the likelihood the same way. Because this wage is just the current period wage, so that part's the same. Okay, this joint probability of seeing you work and having this wage, normally would write as like the probability you work given you have that wage, and then the probability of observing that wage. But those things are all like in the binary example. So I wanted to just show you it's kind of an extension of the binary framework where you just have to have this Emax. Okay, and you also don't need these errors to be additive. So I have some examples, that we don't need them to be normal, they don't need to be additive, they could be anything you want, and they could enter anywhere you want, actually. Okay, but in this simple case, well, it doesn't look simple, I know, it's actually not simple to derive this kind of messy expression, but the unusual thing is that there is a closed form, other than the normal CDF, which is not closed form, but here you can actually write out the likelihood expression. Normally, you can't do that because the models get more complicated, and you would simulate the probabilities. And it's actually easier. I think in a more complicated model where you simulate, it's actually easier to do it that way. Okay? So you shouldn't think that you always have to derive out all these expressions. But the estimation, first you solve the Emaxes, that's solving the dynamic programming. And then once you have the Emaxes, you get the likelihood. Then the likelihood gives you new parameters. And then when you have new parameters, you have to resolve the Emaxes. Because the Emaxes depend on the parameters. So you iterate between these two steps always when you solve these types of problems. Okay, because the parameters are going to determine those cutoff probabilities. So given the parameters, I can say this is the probability, and then I write the likelihood, and then it gives me new parameters. My optimization algorithm will say, okay, move here now, and then I try new parameters. I have to resolve the Emaxes, so that it can be computationally intensive. Okay, that's. But otherwise, the estimation approach is no different from the static model in terms of how you set up the likelihood, and there's only one extra parameter versus the static model. And that one extra parameter is the discount factor. Okay, and also we have these assumptions about how people form expectations about future unobservables. The normality, that we assume the IID. That you don't have serial correlation here. But there is a difference in computational effort here. Okay, but in terms of identification, you still need exclusion restriction. Like if I wanted to do the policy, so let's say I want to do a child care policy, okay? Well, so here's the discount factor. So omega is actually contains all these things, but it's still, you can separate the things because this is a different functional form from here. Okay, but that's the only additional parameter. So there's this one additional omega. Otherwise, you've got like a threshold crossing model the same way. Okay, so what do you think about if I do the subsidy experiment, like the government says what's the effect of a child care subsidy, and one person uses a static model to answer that question, and another person uses a dynamic model. How do you think the results will compare from the two models?
You will have more like women going to work in the dynamic one, right? Because you have this additional argument that in the future you will get more.
Yeah, that there's a benefit in the dynamic model. It's not only that you have currently higher wages, you also have in the future higher wages because it increases your work experience, and you would take that into account. So your response to the child care subsidy is probably going to be larger in the dynamic model because they don't think about just today the benefit, they also think about the future benefit. I think I also estimate schooling models. So when people decide every period you go to school, or do you go to college, do you stay in college, or do you go to the workforce? And in schooling models, you usually have utility from going to school, but the main reason you're in school is not just because you enjoy it. There's some enjoyment factor, but you're mainly in school so that in the future you get higher wages, right? So most people, if there was no wage return to college, I'm sure a lot fewer people would be going to college, right? You expect that you will get a payoff from going to school. So even that type of decision, you could model within this type of framework, just if you go to school or not, where you have a wage opportunity, and when you have more education, then you have a higher wage offer. So it's actually a very similar structure, a schooling model versus this type of model. Okay, what about, because there's another thing that matters, if the subsidy was pre-announced, or if the subsidy comes as a surprise. So let's say the government says in 10 years, we're going to have this child care subsidy. How do you think that would compare versus the government just saying, oh, surprise, now you get the subsidy? Do you think that makes a difference? Like if it's...
Well, that can influence received rates. So the women can decide to work now and then. So.
Yeah. Yeah, so definitely you might want to make this a richer model to incorporate fertility, and then if women knew that they would be getting the subsidy, in the future they might already decide to have more kids because they know childcare will be cheaper. Yeah. I mean, even in this model where if there was no fertility response, they might still respond differently because they might still be more willing. I mean, you don't really know which direction it's going to go, I think, because you might substitute leisure today versus leisure tomorrow. Because, like staying home today, you might stay home when childcare is very expensive and then go work when there's the subsidy. Like if you know in the future childcare, like what if you know next year childcare will be much cheaper than this year? Well, then you can stay home this year and work next year. So if it's pre-announced, you could make those sorts of substitutions, but if it comes as a surprise, then you would make today's decision not knowing that there's going to be a subsidy. Okay? So it matters in these models whether you know a program is coming. And you actually have to solve it differently if the person knows it will be in their budget constraints. So if it's a surprise, you have to solve one model where it's not there at all. They're just behaving as if they'll never have a subsidy. So it's more work if it's a surprise. If they know it's coming, then you only have to solve one model. If it's a complete surprise, you have to solve the model when they don't think it's coming, and then also solve it again when they know it's coming. Most people don't go through the trouble of solving it both ways, but they usually just take a stand, like I think it's a surprise, or I think they knew it was coming. Okay. So pre-announced subsidy, you'd have to solve the model backwards to the period of the announcement, so it matters how you model it. Okay, and there are different assumptions on the error terms that people often make just for computational convenience, because then I would say the main barrier in implementing these models is it requires some skill in programming, because there aren't built-in packages. You have to kind of program your own model. And then also, you need a fast computer, so there's a big literature on how do I estimate these models faster and what assumptions make it easier. So John Rust, he first noted in this early work that if I assume extreme value, so instead of normal, when you model more than two decisions, there's usually a big benefit to assuming extreme values, like Weibel distribution is extreme value. So if I make that type of assumption instead of normality, it's the difference between like a multinomial logit and a multinomial probit. Multinomial logit, so when you have more than two choices, like for two choices, it totally doesn't matter. They're pretty much the same. There's even a mapping between the coefficients. But for three or more choices, it matters a lot. And actually the normal, you can't even do. Like it's computational if you have 5 or 7 choices. That's the maximum you can handle with normality. Because normality, if you have 7 choices, you have 6-dimensional integrals. Okay? Whereas for the multinomial logit, you have a closed form expression. So you don't have to solve numerical integration. So there's a big computational advantage to assuming these extreme value, which gives you logit functional forms. Okay, so I usually have models. I assume normality usually, but this is like in our model we have 2 shocks. So the integral is only over those 2 shocks. So it's not that complicated. If you have 2 shocks, I even have 5 shocks sometimes, and I have normality, but I just want to tell you there are a bunch of papers that assume normality, or assume extreme value too. And then you get closed forms. You don't get integrals. So the Emaxes and everything, it doesn't look simple, but it's actually simpler because you have a formula that doesn't require numerical integration. So there's a big literature this is like solving backwards, solving for the Emaxes. So we don't really have enough time to go over in too much detail how you do this, but sometimes it makes sense to do this, and sometimes it doesn't make sense, really, because for wages, log wages are normal. It's kind of hard to say they're extreme value because it doesn't fit the wage data. You know, usually the reason people estimate log wages is because that's what looks normal. Wages actually looks like Pareto distribution. But like a extreme value would not really make sense for a wage-offer equation. You know, so even if you get computational advantage, it might not really make sense in terms of, you know, what you're trying to fit. So you have to decide whether the benefits in terms of computation are worth the, you know, additional assumptions that may not actually be realistic. But there are different ways people might handle this problem. Like, you could say that the woman decides to participate before she sees her wage, or you could also say that everybody gets the same wage, so there's no unobservable, and that the only reason we see different wages is because of measurement error. And that actually then there's no selection problem. You know, so there are different assumptions you could make that might make it computationally easier. So sometimes if you're reading papers and you say, why did they assume this? Like, it could be that it was just computationally made the problem much easier, you know. I actually use normality a lot, but that's kind of a matter of preference. Like, some people always use these extreme value assumptions. Okay. Now, the thing about having IID, that's also kind of a severe assumption, because wages, there's a lot of serial correlation in wages. You know, you usually have the same job for many years, you know, so assuming IID wage shocks, if you estimate a model with that assumption, you may not fit your data very well. Because the problem is, if you simulate, so what people usually do is you estimate your model, you get your parameters, and then you simulate behavior under your model, and then you look at how closely does my simulation match the actual behavior in my data. You know, so you simulate, am I fitting the proportion of people who work? And then I would normally check, am I fitting the people moving in and out of work? You know, like how many people, if they were working this period, how many people are also working next period? Like the transition probabilities. Because your model should be fitting all those things, right? Because you're trying to fit the microdata and these patterns. And if everything's IID, sometimes you have a hard time fitting transition probabilities. You know, because IID shocks tend to bounce you out. Like you'll be working now, then you get a bad shock, and then you're not working. And if you look in the data, it's not that common for people to be working and then not working and then working. You know, like you don't see people moving around so much. There's a lot of permanence, like state dependence. But like if you're working today, you're probably working at the same job tomorrow, you know? So for that reason, you might want to have some like serial dependence. And there are 2 ways you could introduce it. One way that people use is kind of like a fixed effect, but it's actually, it's more like there are 5 fixed effects in the population and everybody is one of these types. So they call this unobserved types. Like if you ever had to study duration analysis, they use this. This is Heckman and Singer introduced this in durational analysis, and it's commonly used. But it's saying that in the population there are a certain number of types, and people are one of these types. But you don't know which one. So there's unobserved heterogeneity. Like think of there being like a high type and a low type. So the high types are like high ability and low ability. So the high types earn more wages, but you don't know the ability of a person in your data. So it's a mixture model. Yeah?
Now what about these transitory shocks?
The what?
Transitory shocks.
Transitory?
Shocks.
Well, yeah, so there's going to be like a permanent component to the shock, and that's this type component. And then these would be transitory shocks. So these would be the IID component, and this is the permanent component. So this is one way of introducing their serial dependence because of the permanent component. I mean, we could do fixed effects, but if you have 100 people or 500 people in your data and everybody was their own fixed effect, that's 500 parameters you have to estimate. You know, because like a fixed effect model, usually it's linear, you take differences, you get rid of the fixed effects. But in this case, you can't get rid of the fixed effects and differences. You'd have to actually estimate all those fixed effect parameters. So you'd need to have very long panels, and then you'd have one parameter for each person in your data. Okay, so fixed effect models are too many parameters. So this is a way of collapsing people into just a few types, like 2 types or 3 types or maybe 5 types. I think the most I've ever seen is 7 types in a paper. And it's hard to say how many types is needed. Like, you could start with 3 types, and if your model doesn't fit too well, add a 4th type. You know, like people don't usually just start with one model and say, okay, that's it, I'm never changing it. I mean, to be honest, there's this kind of, you estimate a model, you see how well it fits. If it doesn't fit so well, they normally add some parameters, you know, to try and, because it's hard to know from the beginning what is the best model. I mean, it's problematic because it's kind of if you run a regression and some things are not significant and you take those things out, you know, it messes up your standard errors if you do that, right? So technically, you're changing the model in reaction to the data, which is usually not the best practice. But because these models are so complicated, it's pretty common to like estimate the model, you know, maybe see that in some dimensions it's not fitting very well, and then to modify the model in some ways and then resolve it. You know, and usually people would report that in the paper. Like they don't try to cover it up. They say we started with the simpler model and this didn't fit, and you know, so that you kind of learn about what models fit and why one model is better than another. Because we don't really know. There are not that many papers, you know, for each type of thing we're trying to model. Okay, so here, this is just saying you have different types, and that introduces permanence in the errors, and here you can also introduce the same type. And when you introduce these types, you could allow any parameter in your model to depend on type. So you could have like the utility of leisure could vary by types. You could have the wage equation, maybe high ability, low ability get different wages. They could also have different utility. You know, you could put it wherever you want. I mean, usually people just put it like in intercepts. They might have a type-specific intercept in the wage equation, something like that. Okay, and the reason is to capture like permanence and not just have IID. Okay, and the assumption is that the people in your model know their type, but we don't know their type. So from our point of view, it's an unobservable, but it's permanent across time. Okay. And this actually makes our computation even harder because you have to solve the dynamic programming problem for each possible type. So if I have 3 types, that's why people normally assume 2 or 3 types, because it like doubles your work just to assume 2 types. But you solve it for each type, and then the likelihood is going to be the type-specific likelihood, and then here you have a type probability function. So this is normally assumed to be, say, multinomial logit. If you have 3 types, this is the probability of being that type. So it's kind of like a mixture model because your population is a mix of these different types. This is what people call unobserved heterogeneity, like permanent unobserved heterogeneity.
Can I ask one question? How do you evaluate the fit of the model? You undertook this type, the necessary number of types. You just took the look. I mean, you just look the likelihood.
No, what I would normally do is I estimate my model, and then I simulate from my model. So let's say I know the state space for people, and I can use my model to simulate their choices. And I could simulate, because I draw shocks, say, 100 times. So for each person, I would simulate 100 times their decisions. And then I compare my simulations to what actually happened in the data. So like the proportion of people that choose to work, the proportion of people that go from working to not working, for different education levels, for different types of people. And then I say, is my model capturing what's in the data? And normally you would report that in the paper. You'd report your simulations and how that's goodness of fit. Yeah, if you try to get one of these papers published, you have to show that it fits the data well. And if it doesn't, then you have to decide why is it not fitting this part of my distribution? Yeah. Some things are harder to fit than others. I mean, I do some savings models where they're deciding how much of the wealth to save every period. Those are pretty hard actually to fit. But kind of depends on your application. You could also do this. This is the AR1 process on the errors. But the complication this introduces, if I do this, then I have a continuous state variable. Okay? And remember, you need to have the Emax at every value in the state space. So if I have a continuous state variable, then I can't get it at every value, right? And so it makes it harder, because here, this is continuous. So I need the Emax, and this is continuous. And so then what people normally do is they would use an approximation method. Like they get the Emaxes at maybe 1,000 different points and then have an interpolation method, but it just makes it a little harder. So that's why you usually see papers using these unobserved types, because that doesn't introduce continuous state space elements. But that's kind of a complication. But you could do it that way. There are some papers that assume AR1 and then they use interpolation methods for these Emaxes. And actually, I also use interpolation methods because sometimes you may have a discrete state space, but it could be huge. Maybe it's discrete, but it's, 100,000 different state points. And so then you could use interpolation. What people do is maybe you draw randomly 20,000. And then you evaluate the Emax at those 20,000 points, and then you interpolate at other points. So there's actually a whole literature on how you do interpolation. There's kind of a computer science-oriented literature about what's the best way to solve these models and which interpolation methods work best. But it's still a small literature. We don't have all that much evidence on how different methods perform. Okay. Yeah, so having continuous variable creates complication. Then you have to use interpolation. So that's kind of the curse of dimensionality. If your state space is huge, or if you have any continuous variables, then that's a problem. I had this in Mexico, families had a lot of kids in our data set. So they could have up to 8 kids in our model. And then the kids, there were 3 choices, stay at home, go to school, or go to work. So when 2 to the 8 would be, or 3 to the 8th actually, the number of possible combinations for all your kids. So we were able to reduce that by saying you wouldn't send your younger child to work and your older child to school. There were certain patterns you didn't see in the data, so you could eliminate some of those things. But it was still too many possible points, so we had to do interpolation, where you randomly draw some things and interpolate for other things. Okay. I mean, we don't really have time to go into details of how it works, but, okay, and actually Bellman originally talked about this recursive dimensionality problem. Okay. So the two ways to keep it feasible, either you keep your model simple. This is in the US, they have this thing called a KISS principle, which is like keep it simple, stupid. You know, it's like, which I actually think is a good idea a lot of times. It's just keep it simple, because sometimes when you introduce so many complications, you know, it's harder to understand what's going on in your model. So sometimes by just keeping your choice set smaller and your state space manageable, then you don't have to do a whole bunch of, you know, interpolations and then worry if they're good or not, things like that. Or you can abandon the exact solution and then use these approximation methods. Okay, and Keen and Wolpen have some papers only comparing approximation methods. And they show it does pretty well for what they're doing, but you know, when you go to a different type of problem, you don't know if it's going to do as well. And then sometimes with continuous variables, to get the problems to fit these types of models, people discretize. Like I did this in my savings model, because I just said they could save 0%, 5%, 10%, you know, and I made them save on a grid, not to allow every possible savings value. So there are different ways you can make your problem a little simpler. Okay, so these slides, it's just kind of some different methods. So I think these are a little technical that we don't have to go through all that. And there really aren't that many papers comparing. Like there's this one paper that compares a few different approximation methods. I would say there are different methods out there, but there's almost no papers comparing which method is the best. And then in the end, when you do standard errors, you know, because when we estimate things, we do want to get standard errors, and usually you would, if you do maximum likelihood, you just use the standard formula for maximum likelihood. But all those formula don't take into account the approximation methods, because it would be like too complicated to try to account for that. Okay, so that's kind of a drawback of approximation. It's usually not accounted for in the final standard errors. It's not that people don't want to account for it, but it's too complicated. And you can't usually do bootstrapping, because then you'd have to re-estimate your model for like 500 bootstrap samples, and it's already hard to estimate your model for one sample. You know, so unless you have a really simple model, bootstrapping is normally too hard. I wanted to talk a little bit about, you know, how we extend from the binary case to the multiple choice case. So there are different ways we could extend it. More than two choices, because in reality you might want to model labor supply and fertility, you know, like you might have multiple things you're interested in. Non-additive errors, you know, allow log wages and not wages, and then indifferent distributional assumptions and functional forms. So it turns out these extensions are pretty straightforward. And it's kind of similar to the static, like the multinomial case. You get, if you have three choices, then you get two latent variable functions, like these index functions. Okay, so let's see. Here's a richer model. And this is more a model, if you did a binary model, you probably couldn't get it published, because it would be, people would think it was too simple. But this is more the type of model you could probably get published, because it's more realistic, you know. So suppose that we're modeling labor supply, and not only whether you work or not, but also how many hours you work, and also modeling fertility. Okay. So these are the alternatives. Work less than 500 hours, work between 500 and 1499, work between 1500 and 2499, or work more than 25 hours. So now we have dummy variables for these different categories, like D0, D1, D2, D3, and then also fertility. because like a child care subsidy might affect fertility as well, right? And actually, I think fertility you may just want to independently model anyways. Because that's something that's really dynamic, you know, you're choosing when to have your kids, how many kids to have, you know, and I have students working on, like a lot of countries, I don't know if Russia does this, but a lot of countries in Europe give families money for each child they have because they're trying to increase fertility. And so you could analyze those types of programs within this framework. And they may give more money for the first child and less money for the second child, like fertility subsidies. Okay, so normally you would just start off, you wouldn't normally just start off estimating the super complicated model. Like normally you would just look in your data and estimate the non-structural models, like the probability of working, see how it depends on the state variables, just to make sure things actually seem to affect choices. You know, before you go off and spend a month of your life programming, you know, in Fortran or something, you would first want to just use data or some simple, you know, and try and just see, do the state variables seem to affect things? You know, do things make sense in the way that I think they would? Like if a husband earns more money, does that affect the wife's fertility, you know, to get some idea? So this is just relating the choice variables to the state variables. You can think of like probit models and things as just, we call these approximate decision rules. Like you're not actually estimating the full model, but you're just looking what things affect the decisions. You know, and from the model you can get some idea of what should be in omega. So what should I include in my probit model, say, right? So I think that's a good place to start, just by doing those types of models. Okay, and then here would be your utility function, depends on different labor supply choices and on the number of children. Okay, and within these models you normally need a different shock for each choice, for the likelihood to be what's called non-degenerate. A degenerate likelihood means that your model is not able to explain some things in your data. Like if I see something in my data and the probability of that event happening under my model is 0, then that's degenerate. So like if I see two women that are identical, but they make different choices, and my model couldn't explain that, then it would be degenerate. Actually, sometimes macroeconomists have degenerate models because they're not very sensitive to this issue because they're not estimating the parameters and they're not using maximum likelihood. You know, but as a general rule of thumb, usually you need as many shocks as you have choices. So if I have 5 choices, I normally need 5 shocks to avoid degeneracy. So that's why there's a different preference shock for each category of hours. And also a preference for fertility. You know, because otherwise I'd see women that they choose same labor supply, they have same characteristics. One woman has a child, the other one doesn't. So how are you going to explain that? Well, there has to be a shock, right? Something has to explain why she chose to have fertility and the other one didn't. And here fertility is a choice, but I mean, you could also model it as like a random event. There are models even that try to introduce contraception choices, decisions to have sex. Like, you know, it kind of depends on what's in your data set. Like I actually have a project where we're modeling girls in high school in Zambia, and we have data on their contraceptive choices and whether they have a boyfriend. And, you know, so we're getting more into the details of their fertility. I had a student that modeled decisions to get an abortion, you know, because in the U.S. it's a big thing about clinic availability, and some states are making it very difficult to go to a clinic nearby. And so, but in this model, it's just you choose to have a child or not. Like it's not really getting at these details. Okay, and then we can allow some unobserved types. So the budget constraint, now it's going to be a little more complicated. So it's like your consumption, Now I picked the midpoint of the hours. This is the midpoint of those different intervals for how much money you earn. So it's basically discretizing hours. You could do it continuous. Like, I don't want to make you think you have to do it discrete, but if you did it continuous hours, then you have to solve a first order condition every time, for each time period. So it just kind of complicates computation. But some people do everything continuous. All right, this here is like the costs of children. This is the childcare cost. And maybe you have to pay a higher cost if the woman works full-time versus part-time. You might want to incorporate that. Now this here is, okay, so one thing, if you model fertility, these models are not going to capture the fact that people are more fertile at younger ages. It's just easier to get pregnant, depending on the age of the woman. Like the biology, if in women in their 20s, it's easier to get pregnant than in their 30s or in their 40s, just purely biological. And these models don't really have that, of course, like this economics model, how are you going to put that in the budget constraint rate? So you have to kind of put that somewhere because otherwise it's hard to capture age patterns in fertility. And so what people do is you might introduce a cost of having kids or a cost of avoiding fertility in this case, because n equals 1 means you have a child. This is age of the woman, in the beginning, and then this is like her age. So this is a cost of avoiding fertility that varies with age. So it's kind of just trying to capture the biological production function for fertility. There are different ways you could do this. You could just say she prefers more kids when she's young and put it in the utility function. But if you don't have it at all, it's kind of hard to capture some of the fertility patterns just that are biological.
Is it linear?
Yeah, here it's linear, but you could add quadratic terms or, yeah. And then we have a wage equation. So here the wage depends on her schooling. This is in logs, so we wrote this down. It's called like a human capital pricing equation. It's like your wage equals the price of human capital times the quantity of human capital you have. And then in logs, this is the log of the price of human capital, and this is the log of the quantity. And so your quantity of human capital depends on your schooling, on your experience, and on your working decision in the past period. So this is allowing for depreciation. If you lose your job, you can lose some of your human capital. Okay. So this is the wage offer equation, which is now in logs, so it's a little bit more realistic that the error term could be normally distributed in logs. And then...
Do you solve for general equilibrium or?
Well, you can. So there's some literature I haven't really said anything about, but there's some literature that tries, like this is partial equilibrium because the wage, I don't have a model of where the wage is coming from, right? I just said she gets some wage offer. But you could, when you have a decision model, aggregate up all those decisions and then have a general equilibrium equation that says that the wage, like if you have different types of workers, high-skill workers, low-skill workers, and then the wage is like the marginal productivity in the economy. So you have some economy production function and an equation for the determination of the wage that depends on how many workers have like education of different levels. There's a small literature that tries to do that. Like in a static framework, actually it's Heckman and Sedlacek is the first paper in 1985 that did that for a static model. In a dynamic framework, it's a little complicated because when people decide whether to, say, go to school, they have to anticipate. They have to have an expectations process over future wages. So like returns to skill, if there's changing returns to skill, did they anticipate that? And But there are some papers that try to do that, like the general equilibrium versions of these models. Yeah, that's kind of a very frontier of this literature. Like we have some grad students actually that, but I haven't tried to estimate the models yet. There's some complications and additional assumptions in how you form the expectations that you have to do. Okay, and this is saying there's unobserved types. Okay, so this model now has fertility, labor supply, quantity of labor supply, unobserved heterogeneity, so more realistic. You could introduce husband's earnings equation if you have characteristics on the husband. Okay, and then you have kids. You could actually keep track of the children's ages. I mean, that really enlarges the state space, but oops, I can do that. This is experience that depends on work intensity. So you can see it's a much richer model, right, than the earlier one. But again, you could introduce child care subsidies, you could do different sorts of policies. Like in the US, they have something called the Earned Income Tax Credit, which is like a wage subsidy for women that have low wages and they work a lot of hours. Okay, this is actually thought to be a pretty effective transfer program. So you could introduce that here. Like you could introduce, it's kind of a negative tax because you're basically giving money to women that have low wages, but they work a lot of hours. So you could just introduce that in the budget constraints. So that would be a policy you could analyze with this type of model. Okay, so the choice set now, it's more. So you have 8 choices, because you have your 4 labor supply choices plus fertility choice. But then when the woman is older, depending on how long you want your model to run, but at some point, fecund means that she can't have children, no longer fecund. So then she can't have kids, and then she only has 4 choices. Okay. So it's either 8 choices or 4 choices when you're estimating the model. Okay, so then you have utility. The setup, everything is the same. You have current period utility plus this Emax. And in the last period, it's just for 4 choices. These are all the shocks. So you have preference shocks plus income shocks. So these were the preferences for working. This is fertility shock, woman's wage shock, husband's wage shock. So, and usually you would not allow all those shocks to be correlated because then it kind of gets too complicated. So you might just say these are IID, these are independent, and then maybe these could be correlated. Not to have everything be correlated, because that's a lot of parameters if you had, that's 7, so 7 by 7 matrix, and if you allowed all those covariances, it would be a lot of parameters. So normally we impose some assumptions that IID in some ways. Okay, but you just solve it the same way, backwards recursion. This is the state space, it's all possible values of all these things. So there are quite a lot of state space elements. And it's a 6-variate integral over the preference box. Okay, it is discrete, but the dimension is large. So that's why you might want to do some approximation method. I guess you have to, given this, right? It's the number of possible birth sequences. It's huge. Okay. So when I solve these models, so I solve these models a lot, this type of model, it turns out simulation is actually easier than having to figure out all the closed form expressions. Okay, and we solve it backwards. So last time period, the Emax is going to be the expectation over the maximum of these different things. Okay, and this I can solve through simulation. Okay, so what I would do is I would just draw shocks. So this was like the 6-dimensional integral, say, right? I would just draw these 6 shocks d times, mean, let's say you did 1,000 times. You draw these 6 shocks. And then for each set of shocks that you draw, so you figure out what's the optimal utility. Because you draw the shocks, and then that implies something is the best. Right? One of these options is best. Then you draw a new set of shocks, maybe a different option is best. You know, like, but you figure out for each shock which is the best option, and you take the max. That would be their choice under that simulation. And then you take the average, and that's your Emax. So instead of having to like figure out this complicated formula, you just can do it kind of computationally. You just draw the shocks a bunch of times. I mean, you have to make sure D is large enough that you can get it accurate. And this is like Monte Carlo integration. And this is used in other contexts too. So we're basically getting the Emaxes using this integration. And then if you wanted to interpolate, like you only do this for some of the state space and interpolate, then you might do like a linear interpolation. Like you do this at some of these state points, and then for values in between, you could do some linear regression to get at all the possible omegas, if your omega is too big. Okay, so that's what this is. This is saying, suppose you randomly draw a certain part of the state space, like 20,000 out of 100 possible state space points, then you can do like a regression to interpolate. And then you can get the Emax at other values if you need it, you know. Because then when I do the likelihood, I'm going to stick in that person's actual omega. And so I'm going to need the Emax at their omega. Like I look at the person, I say, oh, this person has 3 kids, you know, she has 11 years of schooling, you know, what's her Emax? So, and maybe I never got the Emax at 11 years of schooling, like I only got it at 12 years and at 9 years. But I have this interpolation function that would give me her Emax, you know, at her actual omega. So that's needed when I go to the likelihood. Okay, and so I would just do this, you know, for each time period, I get the Emax at all the different, so this is at t minus 1, but it's basically the same. So right now she only has 4 choices because she's at the end of her life, so she's not doing fertility. But then eventually, so continuing back, at some point it'll include birth as an option, and then it'll be the Emax over 8 choices, you know, when she can have a birth. Okay, and then you can do likelihood, so everything is the same pretty much. But we can also use simulation methods to get the likelihood. So there are 2 parts you can use simulation. You can do it to get these high dimensional intervals. You know, and actually, when I take the mean, that's a very simple simulator. It may not be the best one. There's actually a whole literature on what's the best simulation for high dimensional intervals. There are a lot of papers only about that. So, but I actually use simple ones just because I don't know that literature so well. You know, but I know like one of the guys in my department, Jesus Fernandez Villaverde, works on computational methods for high dimensional intervals. So this whole thing, you know, whether this is the best way to do it, take the mean, it may not be. There may be different ways of sampling, not just randomly, you know. So there are a lot of ways that we don't even know, you know, what's the best way to do things. So the likelihood, we can also do simulation methods. So the likelihood, we want to do this simulation. We want to get the probability she makes a, so let's say I see a woman in my data with this omega. This is her observables. You know, like she has 3 kids and she has a high school degree. She has 12 years of work experience. Like those are all the things that determine omega. And then let's say I see that she's not working and she's not having a child this time period. So I need this probability, because that's what belongs in the likelihood. The likelihood is the probability of observing what you see, right? So I need to get this probability. So I can also do this step with simulation. Okay, I think that's the next slide. So this is how you can simulate it. So I draw m times. So I have, let's say, at this point I have the Emaxes, because remember you have to iterate between. So step one, I already got all my Emaxes. So now I'm at the point where I have the Bellman equation. I have a current period utility and I have the Emax. Well, I draw shocks, like to get the current period utility that has shocks in it. I draw shocks m times, and I figure out what would be her optimal choice under my model, right? And then I look at it, and that's this. This is what was optimal under my model, okay? And if my model is doing a good job, it should match the choice she made. You know, so if my model was like perfectly fitting the data, all the time I should get a 1 here that because in the data she chose 0, 0, and then I'm comparing it to what does my model tell me she should choose. You know, this difference. So this is like an indicator for how often does my model get it right, that this was her optimal choice. Okay, so it's the probability of choosing 0, 0, like given the state space, is through a simulation method. When I draw a bunch of different shocks, it's the fraction of times that my model says she would make this choice. Like you can actually solve even a probit model using simulation. I mean, nobody would do it because it's simple to do a probit model, but you could solve that the same way. You just simulate the utility choosing 1 and 0, and then you look at the fraction of times they chose 1, and you maximize that simulated probability. So this is a simulator of the probability that you choose 0, 0. Okay. And if she chooses to work, then I also have the wage information, because then I have a little more data, so I need this additional piece for the likelihood. Okay, but I can get all those things, let's see, well this is to get just to get the wage equation, but I can do all these things and then, so if you have wages, you need this additional piece, because you see her wage, so you need the probability of seeing that wage. So see, you need the probability she chose, you know, this is missing n, because there should be an n here too, but this is just the two pieces of the likelihood if she's working. Okay, so this is how I would actually solve these equations. So these simulators, these are called frequency simulators. There's a whole literature even on this, on like frequency simulators. And it turns out that it's better to smooth them. Like instead of making it a 0, 1 indicator function, it's better to, they call them smooth frequency simulators. So this is actually McFadden suggested this, the smooth. So he has a paper that just shows instead of just a 1, 0, it's better to do a function that's smoother. So it's, you know, 1, 0 would go like this, right? But if you do something that's smoother, kind of looks like a CDF, that's a smooth frequency simulator. It just goes smoothly to 1 instead of just jumping to 1. And it actually turns out that the smoothness improves performance. It actually makes it do better. So this is what I use. I use like a smooth frequency simulator. I mean, other people use too, but. And you have to set this additional smoothing parameter, kind of just determines the shape of that. Okay, but so there are other simulation methods. You could do simulated method of moments. So the models, I would say the main problem is if you have a lot of choices and a large state space, you know, that you have to do approximation methods, or if you had serial dependence, continuous state variables, you know, those are all like computational problems. You know, but otherwise, in terms of, you know, how you write the likelihood, it's pretty straightforward extension of the binary case. And I put on my website like a problem set that I give. So if you search on my name, you can see my website, and there's like a Fortran program of a fertility model where they're just deciding, do you have a child or not each time period. I just give it as like a problem set. So if you wanted to learn, how to do these models, I think the best thing is to actually try to do a simple model. Like that's just a binary model, and you can see how it's programmed. And then you can change, like in that model there's like husband's earnings, and you can make it steeper over the lifetime, or and see how it affects the timing of fertility and the spacing of fertility. Because in fertility models, you want to have your child early because you want to enjoy them longer, right? Because it's a finite horizon model, so you're not going to have your child when you're 65 if your life ends then, according to the model, right? So it's optimal to have your child early so you can enjoy them for many time periods. But at the same time, when you're younger, you have less money. And so that's why you don't have them all at the same time in the beginning.
Does the model includes adopting children?
Adopt, no. In fact, I don't even know if anybody does has a model of adoption.
Okay.
I mean, you could in principle. The thing is, you'd have to have information on it.
And the previous slide, can we use our targets of the exponential?
I think they're probably different. Yeah, they're probably different functions. But this one, I mean, he's trying to approximate. This is a function that looks like this indicator function. I think this is actually missing. It went off the page. But this, see that indicator function, how it goes 0 to 1?
Yeah.
It's basically, it has to have that shape. So that's why this has that shape. It's a CDF. That's actually the CDF for the multinomial logit. So it has the shape that it goes from 0 to 1. McFadden has a paper where he proposes that. But there are probably other things you could use that would have that shape too. Yeah, and I've had students, do all different types of fertility models. Like one did a model using data from Malawi, where HIV is a big problem, and the women in his data set were getting HIV testing. And he was looking, if you introduce HIV, because people, let's say, if there's no testing, they don't know if they have HIV or not, and they don't know how long they're going to live, and they may assume, actually, he had data on beliefs, because they asked the women, what do you think is your chance that you have HIV, actually? And then they tested them. And so, of course, then they revised their beliefs a lot. Most women learned they were negative. Some people learned they were positive. But actually, in these populations, a lot of times people think they do have it when they don't. So the beliefs normally revise downward when they introduce testing. And he was looking at how that affects their fertility. Because if you think there's a good chance that if you have a child, you won't even be around to enjoy them, and then you find out, and maybe if you think you have HIV, you don't want to have a child and pass it to the child, and then when you introduce testing and then people find out they don't have it, that could affect their fertility. So there are a lot of different questions like related to fertility, Valerie, what time are we going to be done? Oh, now? Okay, all right. Well, sorry, I didn't get to, so if you look at my other lecture notes, because I have another set of notes too, where I have a lot of, just reviewing a lot of different applications of these methods. We got through all the materials about the methods themselves, and I kind of discussed applications, but the second set of slides goes through some different applications, like what were the questions, and, so if you, were kind of able to roughly follow this, you can on your own review the second set of slides and just see illustrations. And then the handbook chapter, covers most of this material too, so that's a good reference. And my website has an actual Fortran program that you could implement and try it out yourself. Thank you.